All right, hi everyone. Welcome to the Chapter 7 practice video. So I'm going to take some problems from the book and adapt them in a way that's going to match the problems you're going to do on your problem set. What I mean by that is I'm going to be taking the data from problem 4 from our book, and I'm going to use that data to solve it as if I was solving problem number 1, which is one of the problems on your problem set. So the data is going to be different, but what questions you're looking to answer are going to be the same. So in problem number 1, you guys are going to be looking at Bicycling World magazine, looking to see if the weight of a bicycle has an effect on the price of that bicycle. And what we're going to be doing in this practice problem is looking at problem number 4 to see if the distance to work has an effect on the number of days that a person's absent. So what you'll start by doing is we're going to insert a scatter chart into the area below. So when you're inserting the scatter chart, we're just going to select the values on this chart here. None of the labels, that's why I just removed the labels altogether. And I'm going to go ahead and insert a scatter chart. And the scatter chart is going to have the number of days. It's going to try to find a title for it, but we're going to go ahead and retitle that to something that fits. So we're going to call it distance to work versus number of days absent. So in your file that you downloaded, the template file, you'll see a spot. You should put the scatter plot. There'll be a shaded area. Go ahead and drag it to that and make it fit. Make sure you add your axis titles, right? The y-axis is going to be in the scatter chart. It always looks to the y-axis to be on the right and the x-axis to be on the left. And that is why your first couple of problems that require a scatter chart are set up where the y variable is on the right side here, but the x variable is on the left side. And that's going to change on the problems where you don't need a scatter chart. And that's because we're going to introduce additional variables. So you're going to have one y variable and then several x variables on some of the problems, because we're trying to look at what could influence the y variables. In this case, what we're looking at to solve is what kind of thing is causing people to miss work. And maybe we're working under the hypothesis that the further you have to drive to work, the more often you are absent, or vice versa. Maybe the closer you are to work, the more often you are absent from work. We're working under whatever hypothesis we're looking to see if we can prove that statistically. So what does this scatter chart tell us? Well, if we're looking at the scatter chart, we see that basically these variables are negatively related. They are sloping downwards. So as the distance to work increases, the number of days absent is actually decreasing. So probably not what we would expect. I would have expected probably the further you are from work, the more likely you are to call out because it's hard to get there. Maybe you don't have a vehicle or whatever. But they found the opposite to be true. Maybe because you are so close to work, you are called in more often when they need somebody to fill in a shift because they know you're close by, and maybe you get burned out quicker, some other reason. So again, make sure we give this a title. This is going to be distance to work. And if you're not sure which one it pulled into the scatter chart, just look at the numbers involved, right? This one goes up to 20, but this one doesn't. This one does go up to 18. This one goes 1 through 9. So that would match that better. So it's kind of easy to tell when you look at the numbers, unless they happen to be in the same kind of range. Number of days absent. So what is this telling us? And we would just answer exactly that. There appears to be a negative linear relationship between the two variables, that the further a person lives from work, the more likely they are to be to have a higher number of days absent, right? That's what we would write in part A. Now, with this next step, it's important that you guys have the data analysis tool pack installed. Now, when we installed Solver for one of the previous problems, I did tell you to go ahead and get the data analysis tool pack installed as well. But if you haven't done that, again, you go to File, you go to Options, and under Options, and again, this is for the Windows version. It's a little bit different. The add-ons are in a slightly different menu. So if you're using a Macintosh, or sorry, if you're using Mac OS, if you're having trouble finding any of the options right here under add-ins, just a quick Google search is your friend there. Just how do I add analysis toolpack? So you click on add-ins, you click go, and then just make sure analysis toolpack is checked. Once you check that, you hit OK, and then it'll just show up right here in the data tab. If it doesn't show up right away, you'll just need to close Excel and open it back up again, but it usually does show right away. So we're going to be using the data analysis tool pack, and we're going to be using the regression tool. So you'll scroll down to find regression, click OK, and here's what you need to know about this tool. One, the Y range. This is what we're trying to predict. We're trying to find the predicted value of Y, right? This is the dependent variable. Y is the dependent variable because it depends on other stuff to explain why it is the number that it is, right? If you're looking to know which one is the explanatory variable, which one is the explanatory variable, is it kicking in yet? X variables are the explanatory variables, also known as the independent variables. They don't describe each other, they describe the Y or the dependent variable. So the Y range, we will include the label at the top here. So the number of days absent, we're trying to predict how often somebody's going to be absent. We highlight all of that. On the X range, and you can click this arrow and drag it over here too, but I usually just click in the box here. Distance traveled to work in miles is the explanatory variable. Make sure this labels button is checked if it's not already checked. And then under output range, the default says new worksheet, but we want to make sure we click output range. And then I've given you the exact cell to click on for your summary output so that it all fits. If you click somewhere else, what's going to happen is that it leaves 3 blank rows underneath and it will delete this out. So if you don't click on exactly the cell that I told you to, where it still says the word summary output, I left that behind, you might lose some parts of your template. And then, you're looking, well, where do I answer part B? Well, you might have clicked in cell A22 instead of A21 or whatever the cell is. And this changes on all of your problems here. So click on the cell that I've indicated. That's where we want to have it kick out. And then we're going to click OK. And it'll say, it will overwrite the existing data. Yes, that's good because I've left the lines there just to kind of show you where it's going to show up. So that's the data it's finding is the word summary output in these lines. Click OK, and it's all going to pop into place. And I do have it set up where you should be able to read on your screen, you should be able to read the names of everything. But if you need to slide it over just a little bit, if it doesn't show up, go ahead and slide it over just a little bit. All right, now let's go ahead and try to interpret what we are finding here. So I have provided you with a file which I've called regression statistics in Excel. If you download that file, it's attached to the problem set 4 link. You'll want to read through that because it helps to explain some of the stuff from the book. It explains what the top portion of the statistics are. It talks about what the middle portion of this output is and what the bottom portion is. So this top portion is the regression statistics. These are also known as the goodness of fit measurements because they basically tell us how well does the model we've created fit the data, or how good of a fit is the data for this model, vice versa. And one of the main things you want to look at in this one is the R² value. This is specifically the goodness of fit for the model. This is known as the coefficient of determination. Coefficient of determination. Be a good music lyric. I won't sing for you. It's too early in the morning. Coefficient of determination is this right here. This is explaining to us effectively how much of the variation in this model, in this graph, can be explained by the X variable. So basically, as much variation as there is in this, it has determined that 71% of the variation in this model is can be explained by these X variables. So basically, something else can explain the rest of it. Something else can explain the rest of it, but distance to work has a pretty healthy relationship. Multiple R is what it calls this factor, but really this is just R. And this is telling us, the R value is telling us how much of a relationship there is, how much we can rely on this number, the quality of the model itself. And 84% is a high number. It's how strong this relationship is. So a value of 1 would be a perfectly one-to-one relationship between these variables. 84% is very good. That's a pretty high number. So good there. Adjusted R squared, similar to R squared, slightly different. This adjusts it based on the number of variables. So for simple linear regression, where there's only one explanatory variable, we're going to look at R squared. And if we create a single model in with multiple variables, we're still going to look at R squared. But if we're comparing two models where we have maybe these two variables in this one, these two variables in this one, these two variables and three variables in this one, it's likely we'd want to look at the adjusted R squared, because it does adjust for the number of variables and inputs. So this would probably give us a slightly better indication, because if I look at a model with two variables in it, it's going to give me an R squared value. And if I throw a third variable into the model and run it again, this number always goes up. It always goes up if I introduce another variable, no matter how bad the data is of the variable. It's just a quirk of the math there. So by introducing a third variable or a fourth variable, I would probably want to look at the adjusted R squared value. And this is something Excel does to adjust that to account for additional variables added. So that's when you'd look at that. We're not going to get into standard error. Observations, 10, this is the N number, right? This is the number of observations or inputs. The next section is the ANOVA section, or analysis of variance. So in this section, if you recall from the other video, the SST, SSR, SSE, sum of squares, these are the number of, the sum of all the errors found, all the residuals found in the model. So this, where SS means regression, that's the SSR value from those formulas. Where SS means residual, that's the SSE, because if you recall, error and residuals are synonymous with one another, but they can't make both of them SSR. So this one becomes SSE in that little acronym. And SST, sum of squares total, well, if you look, these two add up to this. If I was ever to, on an exam, ask you what the sum of squares residual value was, but I didn't give it to you, you could find it pretty easily, because the total minus the regression equals the residual amount, right? Those two added together, 32.69 and 13.3. If I add these together, I'm going to get 46. If I didn't give you the total and I asked you what the sum of squares total was, you could add these together and get that missing value. You could also find in this section, based on these values, what the R squared value is. So if I didn't give you this value, a couple of ways you could do it. One, R squared is R squared, right? So if R squared is R squared and you have R, well, let's just square it. So 0.84312146 times itself, right? Or I can just hit squared, 0.7185, right? There it is. So R squared is the R value squared. If you didn't have the R value and I asked you, what's the R value of this statistics? Well, you could just take the 0.710853812, this R squared value, and find the square root, right? If this is R squared, then the square root of it is R. If I click on this and 8.84312, there it is. Great. How can we find either of these from the ANOVA? What's the relationship there? Well, in this case, I could simply take the sum of squares regression and divide it by the sum of squares total, and that will give it to me. So 32.699275536 divided by 46. So SSR divided by sum of squares total equals 0.71085. There it is right there. Alternatively, I can do 1 minus the sum of squares error divided by total. So do this divided by this, and then 1 minus this divided by this is going to be the same value there. But if you have this value, just this divided by this is going to give you the r squared value. And then from there, you can find the square root of it to find r value. That's a relationship there. You're going to want to know the relationship between these statistics as you're searching for one or the other. But let's get right into what we're going to be doing on this problem. So that was a little bit of a divergence from the problem at hand, which, you know, you're looking to just solve this problem set. Let's move right along. So significance f. This is when you only have one variable. This is the same as the p-value. The p-value is the statistical confidence level, or rather. Confidence level, sorry. It is the sorry, I'm blanking. Confidence level is 95% when that is tested at 5%. It is the significance level, significance level. There it is. So the significance level, what I'm looking at is if I want to be 95% confident that that this variable is a good fit for the inference we're making on the y variable, then I'm going to look at this p-value right here. I'm just going to go ahead and highlight that for us in orange. You can see the values match up here because there's only one variable. What I'm looking at is if I want to be 95% confident, then this value needs to be 5% or less. That's how you evaluate it. So if I want to be 95% confident, then this value needs to fit in that other 5% range. If I wanted to be 99% confident, then this would have to be less than 1%. So if we look at this 0.05, right? 1 minus 0.95. 0.05 would be a 5% significant level. If it was 0.05 or lower, then I could be 95% confident in the value of this. The p-value means that I could, we're not going to get into hypothesis testing because you should have done that in business statistics, but the idea is my hypothesis is that distance to work has an effect on number of days absent. Then if that's the case, then you test the null hypothesis, which is that distance to work does not have an effect on number of days absence, right? And if this is above 5%, then you can accept that null hypothesis and say, nope, it doesn't have any statistical effect on it. But if this is below 5%, then you reject the null and accept your hypothesis, your alternative hypothesis, that it does have an effect on it, and you proceed, right? So this is less than 5%, it's less than 0.05. And so we could say, is there a statistically significant relationship between these tested at the 5% significant level? Yes, there is, because this is under 0.05. It's under that 5% level. How do you know? Because the p-value is 0.00218. And so it is lower than, you know, I would say something like, yes. Should be center here. All right, here we go. Yes, because come on, I want this centered and centered. Yes, because the p-value is 0.00218, which is less than 0.5. So that's where we would start there. And then you'll need to elaborate on it a little bit. the estimated simple linear regression equation. Okay, so the linear regression equation is always going to be right here. Probably hard to read. I'm going to zoom in for just a second. So the predicted value of y is going to be equal to the intercept, the b0, plus the slope times x. Okay, so which one of these is the intercept? What's the value I'm looking at here? So if I zoom in just a little bit, the intercept is going to be the coefficient of the intercept. That's this point. This is at 8.097. So in this formula, what I'm going to write is that y equals this value. Let's go to 4 decimal places. So 8.0978 plus, and it's always plus, even if it's a negative number. So plus, we could write negative when we're writing it here. If you're doing the formula in Excel, you need to do plus this value. All right. So we're gonna write mine. Let's do it right. So plus negative 0.3442. That's the coefficient of the slope, right? So intercept was this one. The coefficient of the slope is B1 value is right here times x, or I can just write x. So whatever thing I'm trying to figure out, and you're going to do that later on. So for example, this is given a we're going to say a distance of 6 miles, predicted number of days absent is. All right, there we go. So what we can do is whenever we want to plug in as a substitute for this x variable, number of days distance to work in miles, or whatever number I plug in, let's say I did 8 miles or 7 miles or 9 miles, it's going to estimate the number of days absent. So I plug in 8.0978 plus negative 3442 times that value. So whatever that value is, and I'll write times or write x either way. But I'm going to jump past part D right here, and we're going to say given a value of, let's just say 7 miles. Okay. So if we give a distance of 7 miles, the predicted number of days absent is basically we're just going to plug in 7 into this formula, and that's going to give us the predicted number. So I did make a note on the very first tab. You must use a formula with references to the correct cells in order to solve this. Well, this 8.0978, that's written right here. This 0.3442, this negative 0.342, that's written right here. So all I have to do is make references to these cells, and it'll create this formula. So the predicted value is equal to this number plus this number times 7. That's the x in this formula. So the intercept plus the slope times x. So whatever value I have x, just write it down somewhere in the cell. And I've given you a spot to do that. But if you're ever doing it again, write it down somewhere and then just hit enter. So the number, it's set to currency, not to general. So the number of days absent is predicted to be 5.69 days, right? And because I've done this with references, if I wanted to know the predicted number of days absent if I lived 9 miles away, 5. If it's 12 miles away, 3.97. So let's say it was 12. It's predicting 3.97, so I would have an error based on what I see here. If I had 14 in this formula, right? 14 miles, 3.28, and well, one person lived 14 miles away and was absent twice. One person was 14 miles away and was absent 4 times. So 3 is the average of that. So it comes out probably pretty close. If we ran all of the residuals of this, we'd probably get pretty close on most of these. And then in your book, let's see, it does ask for part D. It asks us for what the coefficient of germination is. And that's going to be the R squared value. So I would say that for part D, if you're looking at problem 1, the coefficient of determination is 0.7108, which means, let me explain that, which means that 71% of the variation in the model can be explained by the number of by the distance traveled, or whatever it's distance from home, distance to work. Okay, so that would work there, and that's how you do a simple linear equation. So simple linear regression, rather. Use the regression option in the data analysis toolpack, spit out the regression statistics. You evaluate it by looking at this, the p-value. If it's a single variable, you evaluate it based on the coefficient determination, which is right here. You evaluate it based on writing out the linear regression equation. You write this out in text, and then you can actually solve it based on whatever X variable you're provided in your book for that problem. You evaluate it based on the goodness of fit of the model. Again, listed right here, this explains 71% of the variation. And let's move on to the next problem, where we're going to look at a multiple regression problem. All right, for this one, what I'm going to be doing is, you've got problem 9 to do in your problem set. I'm going to be taking just some of the data from problem 10, an equal amount of the data from problem 10, and working that into the problem to show you how multiple regression works in Excel. So in problem 9, it asks you first, basically run it one time with just a single variable. I think on problem 9, it asks you run it with just television advertising, and then run it again with television and newspaper advertising. So in this one, we're going to run it once with just the problem revolves around the overall score, and then how well they rated the comfort, amenities, and in-house dining. But I'm going to keep the number of variables equal to what you're going to see in your problem set. Also, the number of observations as well. So the data is probably going to be pretty wildly inaccurate, since the initial problem had something like 25 observations, and we've cut it down to 8. But we'll just see what happens. So if you remember, because the scattered chart always reads the y variable on the right, it was set up where the x variable was here and the y variable was here. Anytime we're dealing with multiple regression, you're always going to want to have the y variable on your far left. That's because the number of x variables is going to potentially change. All of those are listed afterwards, and that's how these are set up in the book and in the problem set as well. So when you're running your regression with the data analysis toolpack, just make sure that you are paying attention to what the question is actually asking, and that you're selecting the correct variables each time. Don't rely on, let me just show you real quick. If I open up the analysis toolpack, you're going to see it comes pre-populated. Whatever I did last time, it doesn't matter that I switched between tabs, it's still going to be there. So make sure when you're looking for your Y range, what is it I'm trying to predict? Well, I'm trying to predict, in this case, the overall score. What's my X range? It's going to be comfort, amenities, or both. So let's go ahead and change our Y range. Even though it was there, even though it did match up, in this case, I'm still going to highlight all of it and then drag over it. You can also just delete it all out if you want to be extra careful. Labels is selected, output summary range. I don't want it in A21 this time. I want it to show up in A13. And then I'm going to click OK. And yep, I do want it to, oops, yep, see I ran into that problem right here. I can't undo it. 1 second. Yeah, what I did was I didn't move this down. And so I'm going to go ahead. It deleted my pre-written stuff here. All right. That's all right. Here we go. I lost that again because anytime you have it spit out all this stuff, it's going to delete the 3 lines under it. So I need to make sure that there's 3 lines of, oops, 3 lines of space so it doesn't delete the template stuff. All right. So how do we evaluate this? What's the R-squared value? Really bad, it turns out. Only 15% of the overall is being explained by the model. Pretty bad, right? So what do we need to know here though? What's the linear regression equation? So this again was the this formula here. Let me copy it over just to show it to you again. Zoom in a bit. This is the formula I'm looking at. This y equals bx. I'm gonna make it even bigger just to make sure you can see it. That's the formula I'm going to recreate. So the estimated value of y equals part of this. Make this box a little bigger too. We'll do maybe like a 15. Sure. So y equals the intercept. The b0 beta 0 is going to be this number right here, 73.3717 plus the slope, this b1 number, which is 0.1916 times x. And x is just whatever we want to put in. So basically, if I had a comfort score of 89, what would be the overall score, right? Is there a statistically significant relationship between each of the parameters, or rather, in this case, not each of the parameters, between intercept and comfort, because we only tested comfort at a 0.05 significance level? No, there's not. How do we know there's not? Look at the significance F level. Again, it's going to be the same because we only tested one variable. In this case, it's not because it needs to be below 0.05. If you're testing at 95%, this needs to squeeze into the gap between 0.95 and 1, right? Between 95% and 100%, it needs to squeeze into that gap. That's how you can tell this is way above 5%. So the p-value, we're not looking at the p-value for the intercept alone. That doesn't matter to us in this test. We're looking at the p-value for the x variable and the p-value for the model. Again, it's going to be the same because there's only one variable. So is there a significant relationship? No, there's not. How do we know that? Because the p-value of 0.339 is greater than 0.05. And then elaborate on that. The next thing we would want to answer is going to, sorry, and this one, I think it does ask us to find the, how much variation in the sample. So how much variation? Only 15%. R-squared value is 0.1522 or 1523. Therefore, only 15% of the variation of the model is explained by the comfort as the x variable. So that's what we write out in number B in letter B. But then it's going to ask us on question 9, it's going to ask us to run it again. And this time it wants us to use both of the variables. So that's what I'll do here with the problem 10 data. I'm going to run the regression again, but this time I'm going to use comfort and amenities to see if we can improve upon this R-squared value and this multiple R-squared. This is a low value, which means there's not a great relationship, and only a little bit of the variation is explained by it. It's also not statistically sound because it's above that confidence level that we want of 0.05 or lower for that p-value. So let's run it again. We're going to go to data analysis, regression, and our y input range. I'm going to highlight it again every time. And then when you have multiple variables, select all of it in one go. for this reason, and there's going to be a problem in this problem set where you're going to have to rearrange the variables because you're going to run regression something like 4 times total, choosing different X variables each time. You're going to rearrange it to where anything you're going to select, you're going to want to cut and then insert those cut cells to where you're grouping all of them together. You have to select all of them at the same time. You can't select some and then some other ones here and some other ones here. It won't run. You can't do that. So you have to select all of them at once, which we've done. In our output range, we want to make sure we change this. Don't run the regression again and overlap what you've already written. When you're doing it again on the same sheet, make sure you change this output range before you hit OK. Make sure labels is selected. I'm going to have it spit out the multiple regression right here. Actually, I'm going to cancel. I just remembered something, which is because it's multiple regression, there's going to be one more line. I need to move this down one more time. All right, you won't have to do that. That's just on the template here. All right, regression range A44, hit OK, and blammo. So what do we have here? We've got R squared value of 0.2. So that did go up. Great. Adjusted R squared value is negative, which is I don't know if I've ever seen that. This is basically, it's telling us this data is completely irrelevant. It's not explaining anything. You can look at the p-value for the model right here, 0.56. It's gotten much worse. The amenities is not statistically significant. It's way above 0.05. The comfort, even worse when we add in other variables. It was 0.33 before, now it's 0.42. It doesn't know what to think. So this data I've used for the example is showing very high values. But let's say that it was, if we did have data that was in this level, when you're looking at, is there a statistically significant relationship between each of the parameters? You'd want to say yes for comfort, yes for amenities, or in the case of your problem in the book, yes or no for television, yes or no for newspaper. So let's say that television was below 0.05, and I have not run the problem, so I don't know that it is or not. But let's say it was below 0.05. You would say yes, comfort is at p-value of 0.0 whatever, and therefore it's lower than 0.05, so there is. Amenities also below 0.05 plus the significant SF value for the model is over or less than 0.05 as well. So you evaluate all of those terms for the problem here. Is there a statistically significant relationship? And then R squared value, only 20.5% of the variation of the model is being explained by these two scores, comfort and amenities. So that's what we would answer for here. Which model, if any, should we use? In this example, in this practice problem, you shouldn't use any of them because it didn't work out. That might be different on problem 9. Maybe you should either use the simple linear, just use, I think, television advertising, or use the one that includes television and newspaper. You'll determine which one's better. You can do that by comparing the R squared values. And what was question F? Question F. What are the managerial implications of these results? So this is basically knowing what you know from evaluating it. What could you do, in the advertising problem? What would you do if you're the manager? You've seen these results. I want you to answer it like you would a manager. What are the implications of this for operational decision making? All right, we're going to do one more where we're going to include binary variables or dummy variables. All right, on this last one, I'm going to take the data from problem number 12. And I'm choosing problem number 12 because 12 has the conference that the NFL teams play in. And I'm going to do my best to adapt that to show you how to create a dummy variable, which is a binary variable, a 0 or a 1. To turn a qualitative variable or categorical variable into a quantifiable variable. So basically, we're going to create a 1 if it's NFC, a 0 if it's AFC. And in your problem number, let me double check, 13, I believe. Yeah, problem number 13, you're going to be having a repair person who is either Donna Newton or Bob Jones, and you're going to create a 0 or 1 based on that person's name. You're going to create a 0 or 1 whether or not the type of repair was electrical or mechanical. But the problem 13 has several steps, A through F. The first thing it wants you to do is to find just the relationship between a single X variable. So we'll look at the number of yards per attempt for these teams and what the win percentage of those teams were, right? So let's go ahead and run our data analysis regression, and we're going to have it output in this cell right here. The Y range is right here. The X range is right here. And here we go. So it's telling us that based on yards per attempt, there's a decent relationship here. R squared value 66%. That's pretty good. P-value 0.004, well below the 0.05 value that we're looking for. This is 0.04% versus, or sorry, not 0.04, 0.04%, I guess. Yeah. 0.004, we're looking at 0.05 as our metric, well below that. So if I was to write out the simple linear regression equation, once again, you can review. I'm not going to write this one out because you can review that on the previous slides, but it's the coefficient plus this times X, right? The predicted value is always coefficient of the intercept, even if it's a negative number, plus this times X. So we'd write that out right here. Is there a statistically significant relationship? Yes, there is. P-value is this. Now it's going to ask us, after finding the residuals based on the regression equation in part A, do you see a pattern? So what it's going to ask you to do in this problem, and I've got it set up for you to do right here. Basically, I want you to predict the win percentage for each of these teams based on just on part A right here, that alone. So what we're going to do is we're going to take this formula, which is this plus this times X, and X is going to be the yards per attempt. And we're going to predict the win percentage for each of these teams based on their yards per attempt. So how do I do that? Equals intercept. Let's lock that in with our F4 option because we're going to want to drag this down to all the other ones. Plus slope, lock that in, times this one right here, just that top one. So in your actual problem, it's going to be something like months since last service, I think. You would just click right there. So lock in the intercept, lock in the slope, hit enter. That's the predicted win percentage. Drag this down. Now we've got the predicted win percentage for all the teams. Next thing I ask you to do, so basically you're going to want to follow along real close with part B of problem 13 because it's a lot of details it asks you to do there, okay? All right. So next thing I ask you to do is to sort the data in ascending order by value of the residual. Okay, so we need to find the residuals next. Residual is the error. So this is what it would have predicted, but we have the actual value. So we can see how far off our formula is from the actual here. So equals, residual is the actual minus predicted. And it wants us to sort these in ascending order by the residuals. So we're going to highlight everything all the way from the top one to the very last thing under residuals. We're going to go to home. We're going to go to sort custom. We're going to, oops, yeah. Custom sort by residuals in ascending order, so smallest to largest. And we were way off on this one, not that off. And the next thing we want to know is, do we see any pattern in the residuals for the two types of repair? So this residual is way off for NFC. This residual is way off for AFC, NFC, way off for AFC. No, the top two ones are AFC. It was way off. Whether it's way off positive or way off negative, errors are errors. So if we saw maybe the NFC ones were here and the NFC ones were here, but the AFC ones were in the middle, that would be a pattern. We would see they're actually more accurate for AFC than they are for NFC, but that doesn't seem to be the case here. So do we see any pattern? I don't in this one. You might see something in your actual problem that might differ in your problem with the electrical repairman. So do these results suggest any particular modifications? They may not. So, evaluate that, look for any kind of a pattern there. All right, once you've done that, it's going to ask you to create a dummy variable, and you're going to do that twice because in the actual problem, you've got type of repair and repair person. Electrical or mechanical is the type of repair, and then two different repair person's names. This one, I've only got one. So I'm going to show you one time how to do this. And it's a logic test we want to look for. So if this thing right here equals, and then click on whichever one you want to be the one. So if whatever's to my right equals whichever one you want to be the one in the equation. So if I want NFC to be 1 and AFC to be 0, I'm going to click on NFC because I want it to be 1. And I'm going to lock that in. So basically, it's going to look to the right of that cell. And if it finds NFC, it's going to return a 1. So comma, value if true, 1, comma, value if false, 0. It's going to look directly to my right. If it finds NFC, it's going to give me a 1. If it finds AFC, it's going to give me a 0. Make sure you lock in the reference. If the thing to my right equals this particular thing, lock that particular thing in, just that one thing, right? Just this one, the second part of the equals, comma 1, comma 0. So it's going to give us a 1 if it finds it, 0 if it's not. And pay attention to what it asks you in the problem. It says on the first one, 0 for mechanical, 1 for electrical. So make sure it's showing 1 for electrical, 0 for mechanical, and then 1 if it's Donna Newton as your repair person, 0 if it's Bob Jones. All right, so now we have a dummy variable. We also have interceptions per attempt. So I'm just going to do this one time using all of, actually I'll do it twice. I'm going to do it with yards per attempt and interceptions per attempt. And I just want to show you how we can copy, or we can cut this and move it over one time, because you will have to rearrange this. You're going to have to run this 4 different times on your actual problem, I believe it is. And you'll have to rearrange between the dummy variables. You'll have to cut this and then not paste it. Don't cut and paste. You're going to cut and you're going to insert them so that the other ones shift over to the right. So let's run this again. We're going to run the multiple regression with the same y variables, but the x variables are going to be yards and interceptions per attempt. The output range, I'm going to have it output right here, and I'm going to click OK. Now I get a p-value for interceptions of way too high, way too low. I would still write out the regression equation. When you have multiple regression, the regression equation is equal to, y equals, it's similar to the original one, right? Which is here, the y equals this. But let me just write it out and I'll make it larger for you guys. Merge, make it. So when you have multiple requests of them, then you just have intercept plus slope. The first slope of x times x1, so whatever value it is you're interjecting there, plus slope of x2, the second variable, times whatever the second one is, and so on. So in this case, y is going to be equal to the intercept, which is negative 26.0447 plus 13.8108 times x1 plus negative 643.6058 times x2. And if I had a third one, it'd be plus the next one times x3 and so on. So that's how I'd write that. What are the interpretations of all the parameters? Okay, so yards per attempt, p-value is significant, below 0.05. Interceptions per attempt above 0.05, not statistically significant. The r-squared value, if I look at the r-squared value went up to 0.69, but the adjusted r-squared value went down. Again, when we're looking at simple versus multiple, I introduce more variables. Better to look at the adjusted r-squared that adjust it based on the number of x variables. So we've got one x variable here, 0.61, 0.60. So the adjusted r-squared went down. Overall, the model is still sound because the significance level of the model is still good, but interceptions per attempt is really not statistically significant here. It's probably better that we don't use this model because of or this variable in the model, right? All right, let's do it again, but this time I just want to do the conference they're in. So I can cut these, but when I'm going to right click and do insert cut cells, if I paste these, it's going to delete that other variable altogether. I won't be able to get it back when I need to run it with all of them. So right click, insert cut cells, and you'll just swap the places around. Okay. Now I can run this again. So I can go to data analysis, regression. And for my X input range, I can select right here. For my output, I'm going to select the next one down, which is right here, and hit OK. And it's just running it again using the win percentage as the Y variable, and then yards and conference. So now I can evaluate that one. The conference, no good, 0.53, significance level, blah, blah, blah. So for the model, still good. The adjusted R-squared value went down even further from 0.6 to 0.58. The p-value for yards per attempt, we've already shown that to be under 0.05, and that's still the case. So let's run it one more time, and this time I can run it with all three of them. So I'm going to go data analysis, regression, OK. And when I select the X input range, I'm going to select all three of these. So again, that's why you've got the Y variable on the far left when you have multiple regression. So you can group all the X variables together. We're going to output these to all the way down to this one, hit OK. And one last thing, p-value. So now the yards per attempt, because of all the extra information added, it gets goofy. Now it doesn't think it's statistically significant anymore because so much else is being messed with. The adjusted R-squared has gone down even further to 0.53 from starting at 0.61, I think it was. The significance level of the model is now above, just barely, but it's above our threshold of 0.05 when testing at a 95% confidence level. None of the p-values are below 0.05. So if it asks you which model, if any, should be used and why, the only one to pass the p-test, the significance test right here, is the very first one. The yards per attempt is the only one where the p-value remained under 0.05 during every iteration of the modeling for this. It's the only one where the entire model passes the significance test, and it has the highest R-squared and adjusted R-squared value. So for those reasons, you would pick just this one. These results are going to be wildly different on your actual problem, but I hope that shows you how you do that. Again, make sure you do the dummy variables with this formula here. If the thing to my right equals the thing I'm checking for, that it needs to be a 1, comma 0. And when you cut these to move them around, which you'll have to do, you'll cut, Control X or Command X, right click, insert cut cells. Don't paste it. It will delete it completely. All right, long video. That's a long problem to do. But fortunately, I've only included 5 problems instead of 8 this time, just with one of them being longer. So thanks, everybody. And as you have questions, email me. The sooner you start on this, the better. Thanks, everybody.